Hello, chemistry students. Today we're going to talk through some humidity notes. Now, the first thing you'll see at the top of your page here is a list of vocabulary terms that we want to just kind of go through, and we're going to use these in some of our explanations and problem solving. So when we start talking about humidity, we're typically talking about the amount of water that air can hold. So the first thing is dry air, which is when there's no water present in the air. So dry air has no water vapor, which is obviously compared to humid air, which is air that has water vapor. So we're focusing on this idea of water being present in the air. Now, we want to put some actual numbers with this. So the capacity is what the maximum amount of water that the air can hold, and it depends on the specific temperature. So this is the max amount of water that air can hold at a specific temperature. Now, typically we will use a graph that kind of gives us this general trend. So in the previous page of our notes, you'll see we included one of these graphs in your notes. And what this shows us is this is a curve that gives us the amount of water, or water vapor, needed to saturate 1 kilogram of air. And generally you can see the pattern is as temperature increases, the amount of water that the air can hold will also increase. So we've got this kind of general increasing trend. Generally, warm air holds more water than cold air does. All right. Saturated. This is to show when air is fully saturated with water. So that means it's holding, the air is holding, or it is already kind of has 100% of its capacity. So whatever the maximum amount of water that it's capable of holding, it has. The second thing then is dew point. So this is the temperature at which the air will become saturated, or when it reaches its max capacity. So at which the air will become saturated or reach its capacity. Typically you do this by dissolving a lot of water in air, but less than the max, and then you cool that air down. So the amount of dissolved water stays the same, but the relative amount of water that the air can hold decreases, and eventually you reach a temperature where you've reached the max amount. Now, relative humidity is a way for us to describe, well, how much do you actually have compared to what the max is? So this is the relative amount and we're talking about of water again, compared to the capacity, compared to the max amount that it's allowed to hold. And it's a very simple equation here. We take the equation for relative humidity. Sometimes you see this shortened to just RH as kind of an abbreviation here. It's the amount of the amount of water that the air currently has in it, so the amount of water in the air, whatever your current amount is, divided by whatever the maximum amount is, which is the capacity. And because we want it to be a percentage, we multiply it by 100. We have a couple of practice problems that ask us to calculate the relative humidity. So the first one gives us a temperature of 25 degrees Celsius, and it says, use the graph of water vapor in 1 kilogram of air to answer the following questions. It asks us, what's the capacity? So if I go back to my graph here on the previous page, at 25 degrees Celsius, I want to find what the capacity is. So if I look on my x-axis here, I see 20 down here, 30 here. So that means 25 falls directly between them. And I want to look and see where does that intersect my graph. And it's right here. If I draw a line all the way to the left here, right, so I'm lining up my points here. This gives me a maximum capacity of 20. So if I look at my y-axis, this is the grams of water that the air can hold. So if my capacity is 20, and it says if 5 grams of water vapor is in the air, then what is the relative humidity? So my relative humidity is 5 over 20 times 100, which gives me 25%. Sometimes you'll see this on weather reports. It'll tell you what's the relative humidity for any given day. This is telling you how much water is in the air compared to the maximum amount. says if the capacity is only 5 and it tells you that the relative humidity is 50%, then how much water is in the air? Okay, so we've got to work backwards. So I know that my relative humidity is 50%, and that's going to be equal to 5 divided by whatever the capacity is. Oh, I'm sorry, I flipped that. So it says the capacity is 5, and I have to look up what's the actual amount. Well, all I have to do is some rearrangement here. I don't even need to read my graph. I just take my 50%, and I need to multiply this by 100, times 5, and I get my x, right, whatever my amount is, to just be half of whatever my capacity is. So that's 2.5 grams. So it's pretty easy math to do, assuming that you have access to one of these graphs. So how can we change humidity? So relative humidity can be changed in two ways. You can either change the amount of water that's in the air, or you change the amount of water that the air can hold by changing the actual temperature of the air. So we're either changing the amount of water in the air, or we change the capacity, and we do this by changing the temperature of the air. When you increase the temperature of the air, you're increasing the capacity. When you decrease the temperature of the air, you're decreasing the capacity. So it says, what happens to the relative humidity if the amount of water vapor increases? Well, if I change water vapor here, so this is the amount of water that's in the air, if I increase this number, that leads to more relative humidity. I'm increasing the numerator in my little fraction here. This would increase relative humidity. If I decrease the amount of water vapor, now my numerator is becoming smaller. So I'm decreasing the relative humidity. More water in the air is going to cause the relative humidity to go up. Less water in the air causes it to go down. Now, what if you change the actual temperature of the air itself? So this is an opposite. So temperature of the air. If I increase the temperature of the air, what that does is it increases the capacity, which is actually my denominator. So that would decrease my relative humidity. I would be dividing by a larger number. That would make my relative percentage smaller. If I decrease the temperature of the air, that now causes me to have a smaller capacity, a decreased capacity. So if I'm dividing by a smaller number, that would actually increase the relative humidity. All right, why do we care about this, right? What's the whole application? Well, as we know, the temperature changes throughout the day. So if I look at a graph here, this shows me the relative change in air temperature throughout the day. It gives me a graph that shows me the relative humidity throughout the day, and you can see that those graphs are kind of opposites. As the air temperature increases, my relative humidity decreases. I've got my two kind of graphs here plotted along this line. So as the air temperature increases, my capacity goes up, which means I'm dividing by a smaller number, so my relative humidity becomes smaller. And the opposite is true. As the air cools down, its total amount of water is smaller, so it makes the relative humidity look larger. So it says, describe the relationship between the relative humidity and the air temperatures. So this is what we have to put in kind of a nice sentence here. As air temp increases, relative humidity decreases. And again, it all has to do the same, what we were saying on the bottom of the previous page, with changing that capacity. So this goes back to one of those graphs where the warmer the air, the greater the capacity. It says, what can you say about the water content in the air throughout the day? Well, the water in the air stays relatively constant. We're not actually changing what the actual amount of water is. It does change from time to time. Typically, we think about this as changing weather. So fronts are coming through, and we'll discuss this more when we actually talk about weather systems. But the relative amount of water in the air is pretty constant for any particular day. I'm sure we've all gone outside, and on that day, it's a very humid day. You can feel a really high relative humidity. Well, that doesn't usually change, from right before lunch to right after lunch. It's more of a constant. So the relative amount of water in the air is constant. And again, we'll talk about this more, I could say throughout the day, if I want to get a little bit more specific. And we can talk about this a little bit more, and I'm just going to make a note in here. We're going to talk about this a little bit more when we specifically talk about weather and fronts moving through. So we are going to come back to this idea a little bit later on of how do you change this, and what type of weather do we see when you have, you know, a cold air mass meeting a warm air mass, and various things like that, a humid air meeting dry air. So we'll come back to this idea. It says what would have to change in order for the would happen to change the water content in the air, and when would this be most likely? So changing water content in the air would need cold temperatures. So if you can get the temperature cool, you can decrease the capacity of the air, then that will cause, so let's kind of go this. So if I have cold air, this will decrease capacity. And if I can lower that capacity below the dew point, so if I can decrease capacity below the dew point, what that means is some of that water in the air will actually turn into liquid water. It will no longer be able to support gaseous water. So this would then form dew, or liquid water. So now I'm converting the gas into liquid, and I'm actually removing the amount of dissolved water from the air. Now, if I could get really warm air, I could increase the capacity. But what this also does is it allows more water to evaporate. So I could take a body of water, maybe I'm near a lake or an ocean, and I could actually increase the amount of water through evaporation. And it should be no surprise to us that places that are very humid are typically near water. I go down to Florida, it's a very humid place. We can talk about some exceptions here, and it has to do with the actual temperature of the air itself, but this is just big picture right now. All right, explain what would need to happen if the dew point temperature is below 32 degrees Fahrenheit, or 0 degrees Celsius, and the nighttime temperature drops below that point. Well, we just said if you can get the capacity to decrease to the dew point, that will cause the excess water vapor in the air to turn into a liquid. And if I turn it into a liquid below the freezing point, this is what we call frost. You're going to have that excess water is going to turn into dew, and when that dew forms, it's going to freeze. So if you can decrease the capacity to the dew point, you'll have the excess water turn into liquid water, and then the nighttime temperatures will freeze that. So you would wake up and you would see ice on the windshield of your car. It says, what weather conditions, temperature, humidity, wind, favor the formation of dew? Well, in order to get this excess water in the air to then be kind of precipitated out or to be deposited, we need humid air. Humid air allows for lots of water. And what we want to do is we want to have all of that extra water lost. So you need to have humid air, cold temperatures, and if I can get the air to cool down, again, that's decreasing the capacity. And then the last thing is little wind. If I have a lot of wind, it's just going to move that air away, or it's going to evaporate it away. So I want calm wind. I don't want a lot of wind. But I want to have lots of water in the air, and then I want to cool that air down to decrease its capacity, and all that excess dew is then going to be deposited. It says, what time of day is dew most likely to form? Well, whenever it's coldest, because at the coldest part of the day, that's where I'm going to have my lowest capacity. And any excess water above that capacity is going to be deposited. So typically, this is right before dawn. That's when you would find the formation of dew to be greatest. All right, last one here. Explain the relationship between the dew point temperature and the water content of the air. If I can get the capacity to be the same, or if I can, basically change the temperature of the air to reach that dew point, and then any excess water is then deposited as dew, what that's telling me is this is when the air has reached 100% of its capacity. Any excess water is then what forms that dew. So the dew point temperature is when the water content of the air, so the water content of the air would reach its capacity, which is 100%, right? This would be 100% relative humidity. And any excess water is then going to be turned back into liquid. So this is when 100% of the water that's possible in the air is present, and any excess is going to be then deposited on cars or plants or windshields or whatever the case might be. Well, I hope this overview of humidity was helpful. We'll talk more about this tomorrow in our follow-up. Thank you.